When you talk about running Linux on a Windows computer today, two main paths usually come up in conversations among developers, students, and tech enthusiasts. One is running a full native Linux installation directly on your machine, either through dual booting or using Linux as the main operating system. The other is using the Windows Subsystem for Linux, commonly known as WSL, which allows Linux to run inside Windows without replacing the operating system. Over the last few years, this debate has become increasingly important because millions of developers now rely on both Windows and Linux tools. The big question many people ask is simple: does WSL truly match native Linux performance? Or is there still a gap that serious developers should care about? To understand this discussion properly, we need to go back to the origin of WSL. Microsoft introduced the first version of WSL in 2016 as a compatibility layer that translated Linux system calls into Windows system calls. At that time, it was an impressive technical achievement, but it was not perfect. Some Linux applications behaved strangely. Many system features were missing, and performance could be inconsistent depending on what you were doing. Developers who needed full Linux compatibility often preferred running Linux natively or using virtual machines instead. But everything changed when Microsoft introduced WSL 2. Instead of translating Linux system calls, WSL 2 actually runs a real Linux kernel inside a lightweight virtual machine. This architecture shift dramatically improved compatibility, stability, and performance. Suddenly, developers could run real Linux distributions such as Ubuntu, Debian, Fedora, and Arch Linux directly within Windows, with far fewer limitations. The system also integrated tightly with Windows Studio Code, Windows Terminal, and the Windows file system. However, even with these improvements, many people still wonder whether WSL 2 can truly match the performance of a native Linux installation. Benchmarks, real-world workloads, and developer experiences show that the answer is not a simple yes or no. Instead, performance differences depend heavily on what tasks you are performing. Let's start with CPU performance, because this is the area where WSL performs surprisingly well. When developers run CPU-intensive tasks such as compiling code, running algorithms, or performing heavy computations, the difference between WSL 2 and native Linux is often extremely small. In many benchmarks, WSL 2 reaches around 95 to 100% of native Linux CPU performance. This is possible because WSL 2 uses virtualization features built directly into modern processors such as Intel, VTX, and AMD. The Linux kernel inside WSL 2 can access CPU resources efficiently, layers. For example, developers compiling large projects like the Linux kernel itself or Chromium often see compile times that are nearly identical between WSL 2 and native Linux. Some benchmarks even show WSL 2 occasionally performing slightly faster due to Windows scheduler optimizations or memory caching differences. But in most realistic scenarios, CPU performance is essentially a tie. Memory performance is also very competitive between the two environments. WSL 2 dynamically allocates memory based on the needs of Linux applications. And modern versions of Windows have improved how memory is shared between Windows processes and the WSL virtual machine. For developers running tasks such as container builds, machine learning scripts, or large development environments, memory access speeds are usually within a few percentage points of native Linux. However, when we move beyond CPU and memory performance, the story becomes more complicated. One of the most significant differences appears when dealing with file system operations. File I/O is one of the areas where WSL2 can behave differently depending on where your files are stored. If you store your project files inside the Linux file system used by WSL2, performance is generally very good. Reading and writing files within the WSL environment can approach native Linux speeds. Many developers keep their source code inside the Linux home directory specifically for this reason. But if your project files are located on the Windows file system and accessed from WSL, performance can drop noticeably. File operations may become significantly slower because the system must translate between Linux and Windows file handling mechanisms. This overhead becomes particularly noticeable when running workloads with thousands of small file operations, such as installing Node.js packages or building large JavaScript projects. Benchmarks in these scenarios often show native Linux outperforming WSL by a large margin when accessing Windows-mounted directories. In some cases, package installation tasks can take 2 or 3 times longer in WSL compared to native Linux. This is not because the CPU is slower, but because file system translation introduces additional latency. Another interesting performance difference appears in disk-intensive workloads. Databases such as PostgreSQL or MySQL rely heavily on fast disk operations. Native Linux installations often deliver more consistent disk performance because the operating system has direct control over the hardware. WSL2, on the other hand, stores its Linux file system inside a virtual disk image managed by Windows. Although this approach works well in most situations, it can introduce additional layers between the application and the physical storage device. Network performance is another category worth examining. In many developer workloads, such as running web servers, APIs, or containerized services, network speed plays a crucial role. WSL2 uses a virtualized network interface that connects to Windows networking. In practice, this means network performance is usually very good. But there can be small differences compared to native Linux networking stacks. For most development tasks, such as testing APIs, running local servers, or interacting with cloud services, these differences are almost impossible to notice. But in high-performance networking scenarios, such as running large-scale simulations or high-throughput servers, native Linux still has a slight advantage due to direct kernel-level networking control. Graphics and GPU acceleration introduce yet another layer to this comparison. Historically, running graphical Linux applications inside WSL was difficult or required external X servers. But with the introduction of WSLG, Microsoft enabled native support for Linux graphical applications directly within Windows. This means you can launch Linux GUI apps and see them appear as normal Windows. GPU acceleration has also improved dramatically. WSL now supports GPU computing for workloads like machine learning through CUDA and direct TML integration. This allows developers to run frameworks such as TensorFlow and PyTorch inside WSL while still accessing the GPU hardware. In many cases, performance is nearly identical to native Linux GPU workloads because the GPU drivers are designed to expose the hardware directly to the Linux kernel running inside WS. Despite these improvements, some specialized GPU workloads may still behave more predictably on native Linux systems. Developers working on advanced graphics engines, low-level GPU programming, or custom kernel modules sometimes prefer native installations for maximum compatibility. Another factor that often influences developer choices is startup time and system responsiveness. A native Linux system boots directly into the operating system, giving full control over hardware resources from the moment it starts. WSL, however, runs on top of Windows, meaning the Linux environment only becomes active after Windows has booted. That said, WSL startup times are extremely fast. Launching a Linux shell often takes only a second or two because the virtual machine is lightweight. In everyday use, developers rarely notice this difference unless they are performing low-level system work. One area where WSL clearly shines is integration with Windows tools. Many developers rely on Windows applications such as Microsoft Office, Adobe software, gaming platforms, or enterprise tools that simply do not exist on Linux. With WSL, they can keep Windows as their primary operating system while still having a powerful Linux development environment available instantly. Visual Studio Code integration with WSL is a perfect example. Developers can open a project stored inside WSL and edit it using the Windows version of VS Code while running compilers, interpreters, and build tools inside the Linux environment. This hybrid workflow has become incredibly popular because it combines the best aspects of both operating systems. Container development is another area where WSL has made a major impact. Tools like Docker Desktop now rely heavily on WSL2 for running Linux containers efficiently on Windows. In fact, Docker on Windows used to depend on heavy virtual machines such as Hyper-V. But modern implementations run containers directly through WSL2, improving performance and reducing system overhead. For developers building microservices, Kubernetes environments, or cloud-native applications, this integration makes WSL an extremely attractive option. They can build, test, and deploy containerized applications without leaving Windows. However, some advanced Linux features are still easier to use on native installations. Kernel module development, low-level networking experiments, and custom kernel modifications often require direct control over the Linux kernel. While WSL does run a real Linux kernel, modifying or replacing it can be more complex than doing so on a native system. Another difference lies in system administration and infrastructure testing. System administrators who manage real Linux servers often prefer running a native Linux environment because it behaves exactly like production systems. WSL is very close to real Linux, but certain low-level behaviors can still differ due to virtualization. Battery life is another interesting point of comparison for laptop users. Native Linux installations can sometimes provide better battery optimization depending on hardware support and driver maturity. However, modern Windows laptops often have power management systems designed specifically for Windows, which means running WSL on Windows can sometimes deliver better battery efficiency overall. Security considerations also play a role in the WSL versus native Linux debate. WSL runs inside the Windows security model, meaning Linux processes interact with Windows user permissions and file systems. For many users, this integration is convenient, but security researchers sometimes prefer isolated, native Linux systems for testing vulnerabilities or running sensitive workloads. From a learning perspective, beginners often find WSL to be a fantastic introduction to Linux. They can experiment with commands, install packages, run servers, and learn the Linux ecosystem without worrying about partitioning disks or replacing their operating system. If something breaks, they can simply reset the distribution and start fresh. But for people who want to deeply understand Linux system administration, networking, or kernel behavior, running a native Linux installation still provides the most authentic experience. When Linux controls the entire machine, there are no hidden layers or abstractions between the user and the hardware. Community benchmarks across different developer tasks reveal a consistent pattern. CPU-heavy workloads show almost identical performance. Memory operations are extremely close. File system performance varies depending on file location. Disk-intensive tasks sometimes favor native Linux. Networking differences are minor for most users. GPU computing has become surprisingly competitive with modern WSL versions. Because of these results, the real question is no longer about which platform is universally better. Instead, it becomes a question of workflow and personal preference. Many developers today use a hybrid workflow where Windows serves as the main desktop operating system, while WSL provides the Linux development environment. This approach eliminates the need for dual booting and allows users to switch between Windows and Linux tools instantly. Other developers still prefer dual boot setups, where Linux runs natively when maximum performance or compatibility is required. This is especially common among kernel developers, security researchers, and engineers working with specialized hardware. There is also a third group that runs Linux as their primary operating system and uses Windows only inside virtual machines when necessary. These users often value the open source ecosystem, customization options, and control that Linux provides. Interestingly, Microsoft's investment in WSL has changed the Linux ecosystem in unexpected ways. Instead of competing directly against Linux, Microsoft has embraced it as a core part of the Windows developer experience. Today, millions of developers run Linux tools on Windows every day, often without even thinking about the underlying architecture. This shift has also influenced how software companies design their development environments. Many tools now assume that developers may be using WSL, Docker containers, or cloud-based Linux environments. As a result, cross-platform compatibility has become a central focus in modern software development. Looking toward the future, the gap between WSL and native Linux will likely continue shrinking. Improvements in virtualization, technology, storage, integration, and hardware acceleration will make WSL even more efficient. Microsoft has already introduced features such as system support, improved networking, and better graphical integration. At the same time, native Linux will always maintain advantages in areas where direct hardware control matters most. High-performance computing clusters, embedded systems, kernel development, and specialized infrastructure will continue to rely heavily on native Linux environments. So, when developers ask the ultimate question, should I use WSL or native Linux on Windows? The honest answer is that it depends entirely on their needs. If you want convenience, seamless integration with Windows applications, and performance that is extremely close to native Linux for most tasks, WSL is an incredible solution. But if you need absolute control over the system, or an environment identical to production Linux servers, then a native Linux installation still offers advantages that WSL cannot completely replicate. In the end, the real winner in this debate is not Windows or Linux individually, but the collaboration between them. WSL has brought Linux tools to millions of Windows users, making open-source development more accessible than ever before. At the same time, native Linux continues to evolve as one of the most powerful and flexible operating systems in the world. For developers in 2025 and beyond, the choice is no longer about choosing sides. It is about choosing the workflow that helps you build, experiment, and innovate most effectively. And thanks to technologies like WSL, the boundary between Windows and Linux is becoming less of a wall and more of a bridge that connects two of the most influential ecosystems in modern computing.